recording. Okay, we're live, and it's chemistry in the AM. Hope you guys are excited to learn about ice charts. Why ice charts? Because they're so cool. I'm your host, Joel Stelka, and away we go. So, if you're listening right now, live by recording, pause the video and jot this down. Okay, you paused the video. Now you've written it down, let's get going. Ice charts. I'll read through this with you. The problem is, if you're given one equilibrium concentration at a time. Now here's our given information. Initially, we have this amount of NO given, 2 moles per liter. N2 we're given 12, O2 we're given 10. At equilibrium then, we're given oxygen only 7. We've got to find the value of the K here. Now, you're going to form an ice chart. Why ice? Because ICE for initial change in equilibrium. That's where the ice is. So we put in our given information. Initially, there is 2 moles per liter of the NO. So I'm going to put that in. I'm going to use units. Initially, there is N2, there's 12. Initially, there is oxygen, 10. Everything's a gas, so it appears. If everything was aqueous, it would appear in this ice chart. If it was a solid or a pure liquid, it would not appear. We just put a line through that. Now, I have down here this reaction represented here, because I want to show you something. But before I do, I'm going to put in one last thing. At equilibrium, we have 7 oxygens. I have nothing for the change line right now. So that takes care of all of the given information. Okay. So what is this? I'm using blue to represent the nitrogens. O, oxygens are represented by the yellow. Right off the bat, oh, I can't use that. Okay. Anyways, initially, there are 2 moles per liter of the nitrogen monoxide. And if you look, I have 1, and where's the other one? Oh, that's not working well, is it? 2. Anyways, I'm going to erase that in. 2 of those. If you look carefully, I'll undo that. There's 12 groups of N2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pairs of N2, the blue. And there are 10 groups of the oxygen, yellow. Now, somehow, you got to figure out how you go from 10 to 7, right? Well, arithmetic-wise, this is the change, right? It's subtraction, minus 7. So I'm going to write this in here, but then I'm going to represent it with multiples. So minus 3. We know the arithmetic. That's what gets us to 7. I'm doing it in a different color so you know that that wasn't given. So how did that work? Well, if I take away 3 groups of oxygen from my diagram, I break them up. There's 1. I'll randomly place 1 here. 2. 3. I broke up 3 groups of oxygen, right? Now, according to the balance numbers, oxygen's a 1, nitrogen's a 1. For every group of oxygen that breaks up, there will be a nitrogen that breaks up. Does that make sense? 1 to 1, it changes. So this is minus 3 as well. Oh, I guess I'll only use 1. Okay. Now, if I break up 3 N2s, which I'm going to do, 1 apart, 2 apart, 3 apart. Okay, I've just broke up 3 groups of N2, right? At this moment, how many N2s are there? Should be 9 in our arithmetic tells us 9. So 12 minus 3 is 9. Right? Now, what are they doing? This is going to the left, this reaction. Because if this right-hand side is subtracting, the other side is increasing. All of these, you can't just have a lone nitrogen atom and a lone oxygen atom. They're going to form NOs. So I'm going to just randomly take this yellow to move with this one here that broke up, this one here that broke up, this one here, here. If I count these up, now I have, well, let's count them up. How many NOs do I have? 1, 2, 3, 4, 5, 6, 7. I'm missing, oh, I see why. Single. 8. Okay, I'm going to just get rid of the green sticks here that I was just using to count. Okay. I've got 8. Does that make sense from our change column? Well, think about this. If the right-hand side was going down by 3, the left-hand side has to go up. And the balance number on the left-hand side is 2. It's a 2-to-1 ratio. So it changes twice as much, so it should go up by 6. The arithmetic tells me 2 plus 6 is 8. And that is what we had, molecules, right? Now, I did this by individual molecules, but we're actually talking moles per liter. But the math remains the same. Okay? Now, we're not going to do these by diagram, but I just want you to understand what it represents, right? So, is there any questions about this ice chart at the moment? It's a way to organize your molecules so that you can get final or equilibrium concentrations. If you were given one in the first place, not all. Now, I'm just going to erase this, except that it's locked in. Now, doesn't matter. Don't worry about that. You don't need this again. So we're going to continue on with this problem because we were asked to come up with the value of K. That means we need a K expression. KEQ equals products over reactants, N2, concentration brackets, O2, divided by nitrogen monoxide, squared. Then I put in my actual, only put in equilibrium values, my actual equilibrium values. And I'm going to sneak up to that. 8, 9, 7. Now remember this one. 8, 9, 7. Now I could use round brackets there, by the way. You don't have units on a K expression for a K value. It comes out to be 0.9. So mathematically, like I said, I won't continue with the diagram. But the first couple I do with diagrams, just so you understand. pause this video there for a second. Okay, on the recording, live by recording. Copy, pause the screen, copy this example down, go work through it. I'll pretend to copy it down now. Okay. Resume the video, let's go. So here's another example, ice chart, and I will use a visual for this one too. Now, find the KQ for this association of lead to bromide. It's a solid. And I don't give a lot of information here, and this is why I want to show you. We're told, though, the solubility at equilibrium is 0.5 moles per liter. But I don't tell you it specifically for any chemical. First, write the balanced reaction. Now, how did I do this? I had to use an ion chart because I didn't tell you that PbBr2 has a charge of 2 plus for the Pb and Br minus. So use the ion chart if you're not familiar. I've got a 2 in front of the Br negative. What you have to know is the word dissociation is a fancy word for dissolve when you have ionic compound. It dissolves and separates into its charged particles. We'll use the word more often. The next thing is, for an equilibrium ice chart, equilibrium calculations, you never use a solid, so you put a line through there. As those things break up, they don't affect the equilibrium calculation. Yes? What's that? Why did you put the line? Because it's solid. That's right. But it doesn't appear in the K expression. The aqueous stuff does. Now, the solubility is 0.5. What that means is that I don't care how much PbBr2 you dump into this. All of this solid PbBr2, and that's what I'm representing with these this diagram, starts out as a solid initially. Okay? Now, so the initial amount, this is like making iced tea or something. Okay? You initially pour in the powder, the solid. Initially, at the very second you just started adding it, you had nothing of this. Right? Then, this 0.5, what does that mean? It means I don't care how much you've dumped, as long as you've dumped more than enough, 0.5 moles in a given liter will break up. Now, come back to iced tea. If you ever make it, you know, the powdered kind or whatever, you know how like you sometimes think I want it stronger and you add more in there? What happens to the powder after a while? It just sits at the bottom, right? It doesn't matter if you add more. There's only so much the water can take in. Well, that's what this is kind of giving, the solubility at 0.5. I could dump a bunch of PbBr2, but only 5 of these are going to break up. I'm going to use 5 instead of 0.5 because I can. Right. So, 1 of these breaks up, floats around. 2 of these break up. 3 of these break up, floats around. 4 of these break up. 5 of these break up. You guys get the idea there? The rest just sit at the bottom. I could add more, and no more is going to end up in the mixture as a dissociated, separated part. They just sink to the bottom. And this is dynamic equilibrium, meaning every time one of these breaks up, there's still stuff breaking up. This one breaks up. At the very same time, randomly, these guys bump into each other and fall to the bottom, right? The rate of reaction at equilibrium, forward and reverse, is identical. So no net change. So, knowing that 5 of these break up, 0, that there's a 1-to-1 ratio between PbBr2 and Pb, I know that 5 of these will I say 5, I'm talking 0. So 0 plus 0, 5 is 0, 5. The math is easy. Then here, that's a 1 to 2 ratio. There's twice as many, so 0, 10. The math is easy, 0 plus 10. Okay. We know how to do these without diagrams, but I just wanted to show you. Okay, we got this. Now I'm going to do my K expression and plug stuff in. In this case, it's only the products because the reactants is itself. That's PE plus Br minus. That's squared. I want to calculate the K value. So I put in my numbers, 0, 5. Don't worry about units in these calculations. Squared. Now, use a calculator to do this, but it comes out to be 5 times 10 to the negative 4. No unit for a K value. Units are needed for square brackets if you have to solve for the concentration. Pause that.